All right, let's jump right in. Today, we're going to be talking about what the one and only Richard Feynman called the strange theory of light and matter. And he wasn't exaggerating one bit. This thing he called the jewel of physics, well, it's quantum electrodynamics, or QED for short. And get this, it is, hands down, the most precisely tested and successful theory in all of science, period.
So, okay, let's get into it. Why is QED such a big deal? To really get why it's so revered, we've got to understand what it's even talking about.
Think of it like this. QED is the ultimate rulebook for the dance that's always happening between light and matter. I mean, it took two absolute giants of modern physics, quantum mechanics and special relativity, and somehow managed to stitch them together into one single elegant theory.
And here's where Feynman's genius just shines. He managed to boil down every single interaction between light and matter in the entire universe to just these three basic moves. That's it. A photon zips from one place to another, an electron does the same. And an electron can spit out or catch a photon. That's the whole game. Everything from a lightning strike to the Wi-Fi signal hitting your phone, it's all just some combination of these three simple actions. Incredible, right?
Okay, so this all sounds amazing. Perfect, even. But there was a problem. A really, really big problem. A kind of catastrophic flaw that was hiding in the math, and it almost destroyed the entire theory before it even got off the ground.
So, back in the 30s and 40s, physicists were on a roll. For the really simple first-order interactions, the theory worked like a charm. The predictions were dead on. But the universe isn't that simple, right? When they tried to calculate the more complex stuff, all the little secondary effects, the echoes, the ripples, the whole beautiful structure just completely fell apart.
And when I say it fell apart, I mean it exploded. The equations weren't just a little bit off. They started spitting out the answer infinity. Now, what does that even mean? In physics, an answer of infinity is a giant red flag. It's basically the universe telling you your theory is nonsense. It's not just wrong, it's fundamentally broken.
And this wasn't just a one-off problem. These infinities were everywhere. You try to calculate the electron's own energy, just from it existing, boom, infinity. If you try to figure out how the vacuum itself affects things, infinity again. It really looked like maybe the two biggest ideas in physics, quantum mechanics and special relativity, just couldn't play nicely together. It was a crisis.
So how did they fix it? Well, this is where the story gets really good. We're going to see how a few absolute geniuses managed to solve this unsolvable problem with an idea that was, well, it was radical. Some might even say it was absurd.
And what's so wild is that you had these physicists working totally independently, often separated by a world war, mind you, and they all started to arrive at the same completely bizarre but shockingly effective solution. You had Tominaga in Japan and Schwinger and Feynman in the US all circling the same strange idea. And then Freeman Dyson came along and proved they were all just different ways of saying the same thing. It was a total game changer.
Okay, so what was this crazy idea? It's called renormalization, and it's as clever as it is weird. They basically said, okay, we have these infinite numbers messing up our calculations, but wait, we also have these other numbers, like the mass and charge of an electron, that we can't calculate from scratch anyway. We have to measure them in a lab. So what if we just took the nasty infinities and hid them inside those measured values? You just lump them together, renormalize the mass and charge to match what you see in the real world, and poof, the calculations suddenly work.
I mean, even the guys who invented it thought it was sketchy. Feynman himself called it a dippy process, hocus pocus, and my favorite, a shell game. That tells you everything, doesn't it? It felt like they weren't solving the problem, just hiding the pea under a different shell. But here's the crazy part. It worked. It worked perfectly.
And that's the thing. This mathematical hocus-pocus worked. Once they tamed those infinities, physicists could finally let QED off its leash and see what it could really do. And the results? They weren't just good. They were absolutely mind-blown.
Let's talk about QED's greatest hit, its crown jewel achievement. It's the prediction of a tiny little property of the electron called its anomalous magnetic moment. Basically, you can think of an electron as a tiny little spinning magnet, and this number describes precisely how magnetic it is.
Now, older, simpler theories predicted that a related value should be exactly 2, a nice, clean, whole number. But QED, now that it was fixed and working, said, nope, not quite. It predicted a tiny, tiny correction to that number,
It predicted this very specific, very long number. Not 2, but just a sliver more.
And here it is, the big reveal. When they went into the lab and measured it, the experimental value matched the theoretical prediction from QED almost perfectly. We're talking an agreement to something like 1 part in a trillion. To put that in perspective, that's like me asking you to measure the distance from Los Angeles to New York City and you getting it right to within the width of a single human hair. It is without a doubt the most stunningly accurate prediction science has ever made.
So you hear that, and you might think, okay, great, physics is solved, right? Well, not so fast. Because even this perfect jewel of a theory has a few tiny flaws, a few facets that point toward even deeper mysteries.
First off, we have to remember what QED is. It's a theory about light and electrons. It's a masterpiece for sure, but it's not a theory of everything. It has nothing to say about gravity or the forces that hold the nucleus of an atom together. And on top of that, there are some interesting little cracks starting to show up at the very edges of what we can measure.
And the most exciting crack of all involves the electron's big brother, a particle called the muon. It's just like an electron, but heavier. And when physicists do that exact same magnetic moment calculation for the muon, something's off. The prediction from the theory and the measurement from the lab, they don't quite match.
Now look, the difference is tiny. You can see it here. It's a sliver. But it's a persistent sliver. It keeps showing up in experiment after experiment, and that tiny gap between what the theory says and what the world does could be a huge deal. It might be our very first clue, our first glimpse of brand new physics, new particles or forces that nobody has ever seen before.
So that leaves us with a fascinating question, doesn't it? If QED works perfectly for the electron, why does it seem to wobble just a little bit for the muon? What could be hiding in that little gap? This is what's driving so much of particle physics today. It's this incredible reminder that even inside our most successful, most perfect theory, there are still brand new frontiers just waiting to be explored.